I'm going to run the color functions program. Don't use the device for this, since all we care about is the on-screen display. Set a couple of runtime options. One is to make a timeout, so the program will stop after, in this case, 10 seconds. And we're also going to hold the final output to give us a little bit more time to look at what's going on. We're trying to make the red color begin at 20 and go to 100% in 10 seconds, and a formula to make that work should be 8 times t plus 20. And if we run that, you can see it's starting with a very dark red and going to a very bright red as the intensity of the red pixels increases at the rate that we're intending. The next task is to make the green do the same thing, so that in combination with the two we can actually get the appearance to be green, to be yellow. And the simplest way to do that is to tell the green to repeat what the red is doing. And in this case, we can see that both are increasing at the same rate, and that the apparent color on the screen of the color box is becoming the bright yellow now after the 10 seconds. In this case, we want to go ahead and test the efficiency of the operation, and the program is telling us that each time it goes through the 3 calculations, including that blank number for blue, it takes 0.2720 milliseconds. But let's explore some other options for doing it. One thing that we could do, instead of using just the repeat requirement, is to put exactly the same formula in for green as we do for the red. If we run that, we should be getting the same result. Both functions are identical, so that red and green are changing at the same rate, and again we end up with the yellow box. On the other hand, if we check the calculation efficiency of this, it now takes 0.372 milliseconds to go through each one of the calculation cycles. Not very long for an activity like this, but if on the other hand we were programming an airbag controller to go off in an accident, that might be far too long. To explore another alternative approach, we could think about using a recursive function for G, or maybe for both, and to do that we need to set some initial values. In this case, I'm going to set the initial value for the green to be 20, and then use my recursive function if I can figure out how much this is going to increase during each one of the cycles. And another bit of information I need for that is the delta t, the amount of time between calculation cycles. That's 0.05 seconds, which should mean that green goes up by 0.4 percentage points during each calculation cycle. And if I run that, it looks like I do have a valid calculation method. I'm getting the same results, ending up with a bright yellow. And I can again check the efficiency for this, which is now 0.32 milliseconds. It's more efficient than the earlier calculation, presumably because before we were doing 2 calculations, a multiplication and an addition, and in this case for G we're only doing a single addition. It's worth exploring at least one other alternative. To figure out the 0.4, we had to think about the calculation interval. If instead we looked at it that the rate of increase is 8 percentage points per second, and then multiplying that by dt should give us the change during each calculation cycle. So if we run that one, I think we've succeeded in identifying a valid method for doing it. We're getting the same results that we wanted. On the other hand, let's check out the calculation efficiency of this one, and in this case the efficiency is 0.3720 milliseconds, much like it was if I repeated the formula, since there are 2 calculations to be done each cycle. On the other hand, this method does have the advantage that if I were to change the calculation interval, I would not have to change the formula. For a free download of the software, or for more information, please go to www.mathmachines.net.